Thank you very much. Thank you for the introduction. Let's say that this work is actually a sort of report on what I've been doing here in Halmstad, and it was very interesting environment because this is a completely new application area for me. Maybe after all, I'm always using categories somewhere, so I think that's the common thread. And I'm afraid I will take a bit more time than I was advised, but it was a fruitful visit, this one in Halmstad, so I think that's the reason for that. And I have divided the presentation in several parts, so I suggest that at the end of each part it could be appropriate if you have questions, clarification mainly, to interrupt. And since I will be here until the 4th of September, if I take too much time and you want to have cakes, you can ask questions in the rest of the month. Okay? So the first thing that I have to explain is a bit the title. So why should we be looking at a partial continuous map as trajectories for hybrid systems when hybrid systems have been around for quite a lot of time, since the 90s, and therefore a notion of trajectory has already been developed. So the main problem is that the notion currently used is not able to deal with certain kind of behaviors like Zeno behavior and also other like the chaotic one, and I will focus mainly on Zeno behavior. So there are some problems, for example, to have a correct definition of reachability when you have systems with such behavior. So the main point here is to have a notion of trajectory that doesn't have these limitations. The key idea is quite simple, is to say that a trajectory is represented by a partial map, which is continuous when the system has a continuous behavior, and is undefined when the behavior is discontinuous. So this seems more like a way of avoiding the problems. In fact, we will see that there is a way to recover the behavior, the discontinuous behavior in an indirect way. If we want to make a sort of philosophical analog of this approach, mathematical approach, we could say that in this approach, the past influences the future and the present is too short to make a difference. Okay. So in the first part of the talk, I will focus on this notion of trajectory, and then in the second part, I will discuss about reachability and also what can we compute about these reachability functions, since that's one of the main reasons to have tools like Acumen in order to analyze system. You want to compute something that is computable. Right? So we try to set some theoretical limit for that. So the talk will start with some motivating example just to explain this Zeno behavior based on bouncing ball, just to change. Then there is some mathematical preliminaries, and then the third point is the most technical one with the definition of trajectory, and then I will talk about reachability. And actually here I'm cheating a bit about computability because I'm not really addressing the issue of computability. I will look at when such functions like the reachability function is Scott continuous. And the reason to consider continuity rather than computability is that is it simpler, and it's a good approximation of computability because the notion of Scott continuous function was developed to provide the notational semantics to programming languages. And so what you have is that here we have something that it's approximable and will include the computable things, So RE stands for recursive and invariable subset of n. And the behavior of a continuous map on here is completely determined on its behavior on the finite part. Okay? So that's approximable in this sense. So let's look at this motivating example. So in this case, we have a system consisting of a ball that bounces off the ground. So we have two parameters describing the system, the height of the ball and its velocity. And the dynamic is driven by two parameters. One is the acceleration that I assume to be fixed, and then this bouncing coefficient. And in order to analyze the pathologies that you might have at the level of trajectories, I will play with this parameter by see what's happening by changing its values. Anyway, the behavior of the system, dynamic behavior, consists of three rules. So we have the situation when the ball stops, so it's on the ground and doesn't move. So in this case, there is somebody, a football player, that is going to kick it and give a positive velocity. Then there is the situation when the ball hits the ground, but it has a velocity, and it must be a negative velocity, so it's going towards the ground. So in this case, it bounces, and the bounce is influenced by this parameter b that will change. But usually you expect it to be in this interval, the normal physical situation. And then you have the continuous evolution, which is described by this rule. So when the ball is above the ground or is on the ground but is moving up, the movement is described by the gravity, the law of gravity. So you have the acceleration of the velocity, and the velocity is just the derivative of the position. So by changing the value of b, we have 6 different kind of trajectories. So the easy case, when the bounce is perfect, so it's 1 or could be even above, the bounce bounce forever, so there is no strange behavior. The interesting thing is when you have a bouncing factor between 0 and 1. Here you have the first example of Zeno behavior. So here you have that in a finite amount of time, you have infinitely many bounces. At some point, when you reach this Zeno point, the velocity will be 0. The ball will be on the ground, and so at that point, the kick action will take place. And you get this extra velocity. So here is the how the height changes over time, and here is the corresponding situation with the velocity. So we start with negative velocity from 0, and then here we bounce, and then we reach this Zeno point where we get this velocity of 8. Okay? And here I've drawn the picture again. Actually, this one is the most important case, but for completeness, I will briefly mention also the other kind of trajectories. So if this equals to 0, it means that when you hit the ground, this b equal to 0, so the velocity goes to 0, which is this, and then it will be kicked. So we have 3 different states, all at the same time. Before there were only 2 at this continuity point. Okay, and of course, if you look at this, you don't realize that there is this intermediate state. Then, in the situation where b is negative, which seems, from the physical point of view, it doesn't seem very sensible, but we are just looking at a mathematical model, so it's we can play with the parameters. What happens in this case is that the height has the same shape as before, but the velocity has a very different behavior, because here we have an infinite sequence of slowdowns because b is negative. So what we do, we reduce the negative velocity and we keep reducing it until it reaches 0. So we have in this situation at a given time infinitely many slowdowns until it stops and then is kicked. And this is called Zeno chattering, okay? But I will mainly focus on the other kind of Zeno behavior. And then the more pathological situation is when b is -1 or strictly less. In this case, you reach a situation where time doesn't progress because you're never able to move beyond the point when the ball has reached the ground. Okay, so that's the motivating example. So now let me start some mathematical preliminaries. Actually, I will start with a question, just to show that sometimes we need to make the context where we are using more explicit. So here I have a simple question where I have this equation and I'm asking you how many solutions it has. Any offer? Sorry? 2 in the real? Yeah. And that's a good point, because if I just write an equation without specifying in which context I'm trying to solve it, I'm not making the problem clear. I leave it sort of underspecified. So it's important to clarify what is the syntax, or what is the language that I'm using to formulate the problem. So here it seems rather trivial, but actually you can think that x to the 4 is a shorthand for this. So you have a binary operation. And in order for this notation to be sensible, it must be associative. And then the other question is, where do you interpret the language, and therefore what is the space where you can look for a solution? And in this case, so the structure, the most general structure that you can think of is that of a monoid. So you have a set with a binary associative operation and a unit for this operation, which probably is the symbol 1. And now if you think in these more general terms, well, you can always say that x equal 1 is a solution, no matter what is the monoid. If you take the complex number, you get 4 solutions. If you get this monoid, you get infinitely many solutions. Okay, so if one doesn't make clear what is the structure, of course the problem is ill-defined or underspecified. Now, the problem that I want to address is a bit more complicated. So here I want to say what are the trajectories, so the behavior of a hybrid system that is described by these equations, or actually here I could give this sort of constraints on the continuous evolution and the discrete evolution. Discrete behavior or discontinuous behavior. Of course, here I have this prime, this plus, and I have to clarify what it means, and I have also to clarify where this variable x ranges. So in order to make these things clear, I will use some category theory. So I don't need very much, but here I just remind you what is a category. So basically you need to specify a class of objects. In the first example, I will just consider sets, then I will move to topological spaces. Then the other important ingredient is what are the arrows between objects. Usually in category theory one uses this graphical notation, like in graphs. And these arrows have to have some structure, so there should be an identity arrows for each object, and composable arrows should have a composition. Satisfy the laws that you expect from a function composition. Actually, I will consider also some category with richer structure, namely poset-enriched categories. In this case, there is a partial order on arrows, so I can say when an arrow is better than another. And in this case, composition should also be monotonic with respect to the partial order. So let's see the first example of categories that I will use. Actually, I will be using the category of sets and partial maps, but it's useful to see how it is placed with respect to more familiar categories. So the most familiar one is the category of sets and functions and total maps. Then there is the category of sets and relations. So here we have as arrows binary relations, and there is also a poset structure on this relation, which is just subset inclusion. Okay, so that's a poset enriched category. And the category of sets and partial maps is in between the two and inherits the poset structure from the relations, mainly because you can view the function, a map, and a partial map as a relation, namely its graph. And in this case, the partial order is just the extension. The fact that G, so G is bigger than F, it's extend F. So it's, this means that whenever F is defined, also G of X is defined and has the same values as F. Actually, these two posets have more structure, and here it's one way of mentioning Scott continuous maps. So in the case of relation, we have a complete lattice. So every subset of relations has a sup, which is just the union. In the case of partial maps, we don't have a complete lattice. We have something more general, which is called a directed complete partial order. And this means that every subset of partial maps which is directed, so for every two maps in the partial map in the subset, I have something, some other map in the subset that extends them. I have a sup. And the inclusion of partial maps in relations is a Scott continuous map in the sense that it preserves this kind of sups. Okay, now we are going to use partial continuous maps, so partial maps are not good enough. So we have to change category, and we move to the category of topological spaces, which is the natural setting to talk about continuity. So what is a topological space? It's a set X with a topology, which is a set of subsets of X called the open sets, and they just have to satisfy some closure properties, which are very abstract. So one is closure under arbitrary unions and closure under finite intersections. So given a set, you can have a lot of topologies over it, but the topology identifies uniquely the underlying set because it's going to be the biggest open set in the topology. If we look just at the set of real numbers, there are a lot of topologies, but the most the simplest one to describe are the discrete topology. Here every set it's open and therefore it's also closed. the trivial topology that is the smallest one. Here only the empty set and the whole space is open, and again these are also closed. And the standard topology, the one that usually is defined in terms of epsilon and delta, can be defined by saying that a subset of the real line is open if for every element in this subset we have an open ball centered around that element which is completely contained in it. Okay, now, given the definition of topological space, we can define when a partial map on the underlying sets is continuous. So that's the general definition, which says that if I take an open subset in the target space, and I take its inverse image with respect to this partial map, I should get an open subset of the other topological space. In particular, what this says is if here I take as O the whole space, its inverse image, which is the domain of F, must be an open subset of the first space. Okay, so of course, in the case of the real numbers, this definition could be recast in terms of epsilon and delta, but here I want to have a general definition. So now the category of sets and partial maps, they have an analog at the level of topological spaces, which is top and top P. So top is just the set of the category of topological spaces and total continuous map. This one is the category of, again, topological spaces and partial continuous map in this sense. And in this case, we have a poset structure on these maps, which is inherited by the poset structure on partial maps. So, with a picture, we can see the relation between these four categories. So we have a way of forgetting the topological structure just taking the underlying set. So we have these forgetful functors are called. And we have that the same functor here operates well also when we consider partial continuous map. This poset here has the same structure that the poset of partial map has, so it's a directed CPO. And moreover, the inclusion of partial continuous map into partial map is Scott continuous, so it reserves these directed subs. Now, what is so this was one possible definition of partial map. There are at least 4 other definitions that one can imagine in the context of topological spaces, of what is a partial map in topological spaces. But I've chosen this one because it has good properties, and it's actually the natural setting also to talk about solutions for or trajectories for continuous systems that are don't have discontinuities. So the first interesting property is what I called the best partial continuous approximation, which says that every partial map, it doesn't have to be continuous, has a best partial continuous approximation. And what it means best? Well, it means that for every other partial map between these topological spaces, which is included in the not necessarily continuous map F, there is this particular partial continuous map that includes G. Okay, so among the partial continuous map that are included in F, this one is the biggest one. Well, let's see some example of what are these best partial continuous map in some simple cases. So the first two are actually total maps on the reals. So this one is the map that assigns 0 to every rational number and 1 to every irrational number. Its best partial continuous approximation, well, is the map that is everywhere undefined. And the problem is, or at least the way to understand that, is that no matter what x you choose, if you take a small open subset containing x, this function is not continuous on this small open subset. So this other situation, this other function is more well behaved, so it's 0 for negative numbers, 1 for positive number, and there's some value y when x is equal to 0. Okay. So this one, the only problem could be when x is equal to 0, and in fact here is not continuous, so the way to make it continuous is to make it undefined at 0. Then here I have a partial map, so that's the partial map, which is the square root when x is not negative and is undefined when x is negative. Now this seems to be continuous, but in fact doesn't fall into the definition of partial continuous map. The problem is again 0, because if I take 0 and I take an open interval containing 0, of course the negative part of that interval, it's undefined, so it's not continuous there. So I have to remove 0 from the domain to make it continuous. Okay. So what can I do by exploiting this property? Well, basically that's a way of making every function on R that for some reason is not continuous, I can make it continuous. For example, I can use this smoothing operation to define derivatives. So the derivatives could be defined for functions that are arbitrary functions. Of course, to make the definition make sense only when the function is continuous, at least in a neighborhood of that point. But the derivative itself could be defined but not continuous. And actually the only interesting situation is when the derivative exists and it's also continuous. So somehow what you can do here is to say, well, I start from f, that it's partial, total, I don't care, may not be continuous. I apply this operation and make it continuous. I compute the derivative in the usual sense, I get something that may not be continuous. I reapply this operation and make also the derivative continuous. So I can ensure that the derivative is always a partial continuous map on R. Then at this point, I can recast what I mean by a solution to an initial value problem. So here I'm saying I want to find a function, but what kind of function? X, that at 0 has this value and satisfy this differential equation. So here, by solution, I mean a partial continuous map that is defined on 0, and for every t in the domain of this partial continuous map, so this will contain at least a neighborhood of 0, it satisfies this equation. Okay? So here it's only in the domain that I require that to be satisfied. And so this means that the derivative has to be defined, has to have the same domain as x. And f, of course, should be defined as well. Okay. If there are no questions, I will pass to the definition of trajectory for hybrid systems. So I will use a very simple definition of hybrid system, but it's good enough to make the point about the use of partial continuous map. So by hybrid system over R of n, so a n-dimensional vector space, I mean a pair of relations, f and g, f I call the flow relation and g the jump relation, and that's it. Now I have to define when a partial continuous map from where? From the timeline, so here the trajectory is how the system evolves over time. From the timeline, which I identify with the real line, and the space S, which is this n-dimensional vector space, when such a partial continuous map is a trajectory for this system. Of course, here you will depend on f and g. Let me point out that for a partial continuous map over the reals, the domain has a very simple structure, is the disjoint union of open intervals. Okay. That's what it is. Now, the F part, the flow part of the hybrid system, tells me how the trajectory H has to behave where is defined. So it has to satisfy this differential inclusion equation, I mean, this constraint. So the derivative has to be defined and has to belong, to be related to h of t through this flow relation. So what is the role of G then? The role of G is, it's a bit more difficult to explain, but will be to explain how the different section of H on this disjoint open interval should be glued together in order to represent a trajectory for the hybrid system. And here I will make some simplification, so I will assume that this relation G is actually reflexive and transitive. Okay, so this is actually probably the most complicated slide. So I have to define, I will define first what is a trajectory of some length of time. So this is just the constraints related to F, which I've written before. So let's focus on the constraints related to G, the jump function. Now, in the case in which the length of the trajectory is 0, this means that the trajectory is everywhere undefined. And so there isn't much to say. That's it. It's a trajectory. The everywhere undefined function is always a trajectory. On the other hand, if it's not undefined, and I look at the domain of H, so that's a non-empty set, it will have an inf and a sup. So I will have to say something about the behavior of H in this open interval. Okay. This open interval could be also minus infinity plus infinity, of course. Now this this open interval contains the domain of H, but there could be points where H is undefined. Okay, so G is mainly telling us something about this point where H is undefined. Of course, since H is undefined, it doesn't make sense to put some constraints on the value of H at this point, but I can talk about the value of H before that point, that's this notation, and after that point. Okay? So, what do I mean by this? This is the set of accumulation points as I approach the time t from before. Okay. And this other notation, it's not the set of accumulation points, but it's the limit of h t prime as I approach t from after. So let me clarify the situation by recalling this behavior that was the velocity of the bouncing ball. So here what happens? Here we have this discontinuity, so the function is not defined here, but the accumulation point from before it's going to be this value, and the limit point from after is this value. Okay. This happens for all this interval, but now let's look at the Zeno point. Now in the Zeno point we have, of course, the limit from after, which is as before. But here, do we have a limit or an accumulation point? Because so far, these one are also limit. So this is the value 0 here is not the limit, but it's the accumulation point. Here it happens to be just 1. Because the problem is that when I take an interval here, actually something an open interval that ends at the accumulation point. Here I have infinitely many points where the function h is undefined, so the limit is not well defined. And I have infinitely many points where h is defined. And so it makes sense to talk about accumulation points. Okay? So that's the reason why I have to use this asymmetric definition. So the past is handled in a different way than the future. Okay, so that's the most important definition. Then in order to define reachability, I have to consider, to define when a trajectory, h, of this, in this case of finite length, goes from one state, from the initial state to a final state. Now the problem is that the definition of h is undefined at some limit points. So, for example, when h is the trajectory of length 0, actually connects, may connect two states, and it connects two states exactly when they are in relation G with each other. So it's only when from S0 I can jump to S1. Okay. So there are a lot of them, there could be a lot of them, H is always the same, and it doesn't provide me information about S0 and S1. Okay. Now let's try to clarify, at this point I have enough definition to clarify in what sense the standard definition of trajectory is not good enough to deal with Zeno behavior. So let me recall that the domain of a partial continuous map is an open set. Every open set of a real line is the disjoint union of open intervals. And if I have a disjoint union or a family of disjoint open interval, I can define a linear order on these intervals, which is just this one. So I'm saying that one interval is before another one. They could touch, or better, they could be adjacent. They don't touch because they are open. And so here I have a linear order whenever I have a disjoint, a family of disjoint open intervals. Now, when H is not just a partial continuous map, but is a trajectory between from S0 to S1, this linear order has more structure. It's an ordinal. So of course it could be 0, so it's empty. Ordinal is 0. If it's not empty, then it has a minimum, which starts from the inf of the domain of H. Every element which is not the last one, because it could be a finite ordinal, as a successor, and the successor is always adjacent to the predecessor. Okay, now the trajectories that are usually used in hybrid system, they correspond to ordinals that are less than or equal to omega, which is the first countable or non-finite ordinal. Okay. So of course this means that they can get very close to this Zeno point, but they can never reach it, not go beyond. Okay, so now I will talk about reachability. And I will start with the obvious definition of reachability. So I have a notion of trajectory. I've defined what it means for a trajectory. So here it doesn't really matter so much at this point whether it was a partial continuous map or something else. From going from a initial state to a final state, so I can define, say what is the set of states reachable from a set S of initial states by simply saying I take all state S prime for which there is a trajectory from a state in S to S prime. So that's the obvious definition. This function, it's a function on the subset of the state space. It's monotonic because, of course, the more initial states I have, the more states I can reach. And it's also idempotent. So what I can reach from reachable states is going to be reachable. That seems to be the obvious definition. However, we are in a topological setting, so there are the reachable states, and there are also states which are very close to reachable. Now, since reachability is mainly used for safety, you want to be a bit cautious and say, well, maybe if I just got some parameters wrong, what is not reachable but is very close to reachable, maybe is reachable. So you might want to use a safer notion of reachability that consider reachable also what is very close to reachable. And then this suggests a different notion, a safer notion of reachability, which consider not just arbitrary subset, but closed subsets of the state space. So this one, how is defined? Given a set S, a subset S, and we can assume here that it's closed, but it doesn't really matter. We take the smallest, and here it's important, closed subset of S, which contains the initial states, and is closed under reachability. Okay. Now this definition is safer. It is still idempotent. It includes the previous definition, and actually it includes the closure of the previous definition. So by this overline, I mean the smallest closed subset containing this set here. So one may wonder, if we take this safer notion of reachability, how much stuff we add. Now here I consider a very simple system, something that doesn't have any Zeno behavior, but it has some discontinuities. So that's a system with exponential decay. So I have a mass m. So it's actually here, and it decreases exponentially. So this equation. And when it reaches 0, I refill and I put this mass equal to 4. Okay. Now, since this is an exponential decay, if I start from some m, which is strictly greater than 0, I will never reach the value 0, so I will never do a refill. So the unsafe notion of reachability will tell me that if I start from a mass which is between 1 and 2, I will reach a mass between 0 and 2, but excluding the two extreme points. Of course, if I take things that are very close to reachable, I will include also 0 and 2. Which is what I do here. But if I consider also 0 and 2, but the main problem is 0, reachable, because it's very close to reachable, then this jump will become effective, and so I will add much more stuff than just 0 and 2. I will add all these elements. So the difference between an unsafe definition of reachable and a safer definition is quite large in this case. Okay, now I'll look at computability issues and computability issues for the reachability function. Okay? So we have this map, I call it R, but actually here I mean either this R or this safer R. They are both monotonic. Okay. Are this map Scott continuous? Or in other words, are they approximable with arbitrary precision? And I will not care at this point about computability. And of course, if the answer is no, they are not Scott continuous, then there is no point in trying to compute them. Okay? Now, one first issue to address is what kind of functions or sets are we going to consider? So, in the case of reachability, I was taking any subset of the state space. for the safer notion of reachability, I consider the closed subsets. Actually, a better choice is the one, for example, used by Edalat and Pattison when they define the denotational semantics of hybrid system, is to take the compact closed subset of S, which in the case of Rn means the closed sets which are also bounded. So I will focus on this partial order. And now the other question is, when defining the Scott topology, we have to decide what is the partial order on these subsets. Of course, the most obvious partial order is subset inclusion, but Scott domains should be understood in terms of information. So one should say when some subset provide more information than another, and in this case information means more precise information about a state. So in this case we should take as partial order not inclusion but reverse inclusion, because the smaller the more precise information I have. So if I take reverse inclusion, it means that computing the sup is taking intersections. And that's a good choice because, for example, closed sets are closed under arbitrary intersections. So intersection of computed here, and also computed here is the correct way of computing the sup. Now, I've defined what is my desiderata, so it's to have a function that is Scott continuous with respect to that particular choice of partial order. In fact, we will see that usually they are not Scott continuous. So what can we do? Well, it's my lucky day. Also in this case, if things are not continuous, there is a way of making them continuous. So there is a best way of making them continuous. So of course, here I'm not applying the same result as before, because before I was talking about partial continuous maps. Here I'm talking about monotonic maps, and I would like to make them Scott continuous. So the setting is a bit different, but the flavor of the result is the same. So somehow what I want to do is to say I have a monotonic map between partial order in general, but I will have to make some restriction there. Is there a Scott continuous map, a best Scott continuous map that approximates this map F? So it means that this one should be less than or equal than F. Now here I take as order on the monotonic map, so here are total monotonic map. I don't take the extension order because they are defined everywhere. I have to take the pointwise order. So in this setting, we are assuming that Y is a complete lattice. The poset here on monotonic map is the pointwise order, and the same in the case of Scott continuous map that are necessarily monotonic. So we have this result. So in case our reachability map is not Scott continuous, we can use this trick and replace it with something that is Scott continuous and less precise, of course. Okay, so let's, I was saying that I'm going to focus on this one, this complete lattice of closed compact subsets. And actually the inclusions of this lattice into the lattice of closed subsets or all subsets, they are all well behaved, they are all Scott continuous. There is also a way of going back, but that's only monotonic, it's not Scott continuous. And actually, if I try to take the best continuous approximation, I will get something trivial that maps everything to the least informative element. Okay. So we said that we focus on this complete lattice. Let me give you some intuition about what it means to be Scott continuous in the case of just the lattice of a compact set on R. And actually, I'll make an even simpler example. Let's consider this singleton. So this is compact, very simple compact set. Now, a monotonic map is Scott continuous in this point if for every closed interval that contain X is in the interior, so it is strictly less and strictly more, the set, so this F gives me a compact closed set, is obtained by intersecting all these sets as this interval shrinks more and more towards X. So it can never be X because X should be in the interior. Okay. So the interesting thing is that, for example, the definition of safe reachability that I gave you before, restricted to compact subset, even for very simple systems that have no Zeno behavior, is not Scott continuous. Okay. So it's not Scott continuous. Here it's again the same example as before, the decay, but here in order to make the case I need to add another variable, which is a timer. So here I'll show you what kind of extra stuff you need to add if you want to make this safe reachability function Scott continuous. So the critical point is here. So let me explain what this system is doing. So we have a timer, and the timer just decreases. So we put a positive value to C. Decreases linearly, and the mass decay exponentially in an exponential way as far as the timer is greater than 0. When the timer becomes 0, there is no rules, so the system stops. Okay. When the mass goes to 0, as before, we jump. And here the timer doesn't change in that case. So let's consider what happens here. So we start with 0 mass, and we have a time unit. So we apply this rule. So we refill. We start with 4, then we start decaying. So that's what the set of reachable states. So we have the initial state, and that's the other things that are reachable. Here there is no problem of adding very close to reachable because I never go close to 0 because t stops after a unit time. But what is the best Scott continuous approximation? Well, the best continuous approximation is to add some additional points that come from the fact that when instead of 0 I have some positive mass, and therefore I have this sort of reachable states. When m goes to 0, well, this one goes to 0, and that's the limit that I reach here. Okay, so I have to add this red part. So that's the price I have to pay if I want to get something that is continuous and therefore has a chance to be computable. In fact, there is another issue that I don't know, maybe we'll consider whether to address it or not, that this Scott continuous map may not be idempotent. And actually, in this case, it's not idempotent. So if you expect to have the properties of something like a reachability relation, you may want to consider something even bigger than that. Okay, so I think I managed to stay within a reasonable time, so let me conclude. So we have given a notion of trajectory that is able to cope with Zeno behavior and also other problems that are not adequately addressed with the current notion of trajectory. We use this notion to define a reachability map, and we saw that the definition of reachability was not completely obvious, that there is more than one definition. And then we discussed computability issues or approximability issues about this reachability map, which is quite important for the point of view of analyzing systems. And we observed that actually it's, in very simple cases, it may fail to be Scott continuous. Luckily enough, we have a way of preparing this situation. So we say it's not Scott continuous, but we may approximate it using the best Scott continuous approximation. So I use these two results that are quite general and maybe they are useful also in other contexts, which are this best approximation. Of course, what I should stress is that best approximation doesn't mean that it's very good. So we saw that if you add this spurious element, you can get something much bigger, both in the case of a safe reachability function and in the case of the Scott continuous best approximation. Okay, so that's it. Thank you very much. Okay, so the question was why we have this asymmetry with respect to time, with respect before and after. So I must say that I'm not a physicist, so I cannot answer from that point of view. In the case of systems like say this system here, it's quite clear that there is an asymmetry here, and somehow the intuition that at least I have is that when I have an initial state, it could be this one, then I jump, then I want for at least a short time be able to predict what the system is doing. So I want something that it's continuous in a small interval after the discontinuity. But before the discontinuity, I mean, there are these Zeno points, so even if each of these, so here you could say that here I could require that for each interval, I have both the limit here and the limit there. So I could make this additional restriction. But when I reach the Zeno point, this is not the upper bound of an interval. That's the problem. And so there is this asymmetry. So you could make a more general definition of trajectory where you say so I could make a more, so the sort of behavior that I allow with that definition is to have a situation where I reach a point where here I have an interval of accumulation points, but I forbid to start from a state, and here I have sort of things that start in a chaotic way, and then maybe they stabilize. So I think that the intuition for allowing this, but not this one, is that if I have an initial state, somehow I should be able to predict the behavior of the system for a short period. And if I have a behavior like this, that's not possible. So the question is, when we deal with computability, well, the first thing that we would like to be computable with respect to is the description of the hybrid system. So that's definitely a good point. I don't have an answer in the sense that somehow when you want to describe an hybrid system, you go to a higher level of functionalities, right? So there could be an issue of what kind of representation do you use for a hybrid system. So in the case of Edelat and Pattison, they have make precise choices. Of course, if you make that kind of choices, you rule out things like Zeno behavior, which is something that I'd prefer not to rule out. So I don't know, so I cannot answer to that question, but certainly it's a relevant issue to make precise what is the class of, or the Scott domain, say, where the hybrid system live, because that's a point to say, is this hybrid system that maybe is this continuous component approximable in some sense? And unless I specify that, I cannot answer your question. Yeah. So the question is whether the definition of reachability could be given more directly in terms of F and G rather than going through trajectories. I suspect it should be possible. I haven't thought about it. I have the impression that the definition of reachability that Edelat and Pattison have, they exploit the description of the hybrid system. So there, of course, they assume that it's continuous, so you can work in the setting of domain theory, and therefore they can define reachability. Well, actually, they define reachability also as a function of time, as a continuous map obtained as fixed point of some continuous functional. So I guess it should be possible. The problem is that in this setting, I've been very general. So here I'm assuming F and G to be arbitrary relations. So in this case, probably I will have to use just any subset of S and try to devise a direct definition of reachability working on that. And probably should be possible. Okay, so the comment was that this talk has been mainly on the notational semantics, but of course one is interested in operational semantics, which should be computational, computable, and at least this one provides a sort of correctness criteria. So you expect that the operational semantics should approximate in a computable way whatever the denotational semantics gives. well, actually, this definition of derivative is really playing with the traditional definition of derivative and this operation to transform something that may not be continuous in something continuous. So the key point, if you look at what they do in analysis, they define the derivative, and then they typically assume that the derivative they have interesting theorems only when the derivative is also continuous. So usually you have this class of functions, which is C1, I think is written that way, which is the functions that are continuously differentiable. And so in that case, you are saying, I start already with a continuous function, and I want to be differentiable, and the f prime should be also continuous. So in that case, applying this best partial continuous approximation would be irrelevant. So this operation, it's a way of forcing things to be well behaved if for some reason they are not. So you could have situations where they are not well behaved. So the comment is that Edalat in 2013 introduced a notion of derivative for Lifshitz functions. Okay. So the first question was why I do this. I guess to have a semantics that makes sense of systems that have Zeno behavior and other pathologies. And I think it's important to address this kind of problem because when you have a formalism like the one used for modeling hybrid systems, of course they are mathematical formalisms. They have a semantics. They may not correspond to physical system, but when you devise computer-assisted tools to analyze these mathematical models, you should make sense of what the mathematical model is saying. And so if it has a behavior that is not what you meant, you should be able to say that it has this pathological behavior, rather than saying, for example, in the case of reachability, that it's a safe bet to point all your money on the turtle because a killer will never reach it. I mean,